All right, so we're moving into our third unit. Now, on its face, this third unit of acids and bases looks a little bit more deep and long than either of the previous two. This is a bigger chapter in terms of the number of sections that are in it. However, what we're going to see is that the majority of these sections are short. And a lot of them are review or extension of what we learned about acids and bases in Chem 105. So from that standpoint, we are going to spend most of our time today on these first 6 sections. Most of our time on Monday will be on these 3. And then we'll be wrapping up on Tuesday with the last 3. And so what I want you to keep in mind, and again, this is a prime opportunity where if there is something that I'm talking about that is, something you remember or just need a little bit more context on, don't be afraid to stop and ask about it. Because there are going to be some things that are familiar, but there are also going to be some things here that are different. And we got to make sure that, after we leave today, we kind of have a good fundamental understanding of acids and bases so that we can do the heavy calculation work next week. So the chapter begins with a question here, and the question is this. We've been able to track the amount of carbon dioxide in the atmosphere, and we've been able to do so for several decades now. And it's not a particularly difficult kind of proposition to recognize that the amount of carbon dioxide in the atmosphere is increasing. That is a verifiable fact. And what's more interesting about the fact, to be honest, is that the graph itself shows that there is a yearly cycle that takes place. The carbon dioxide concentration peaks somewhere in late spring, early summer, and kind of craters right around the beginning of fall. And it goes back and forth, up and down throughout the year in this same kind of cycle, regardless. Well, that increase in carbon dioxide has led to an increase in the acidification of the water. The pH of the oceans is decreasing. It is becoming more acidic. And depending upon where you look, you can see that, for the most part, the oceans in kind of the equatorial zones are changing about 0.06 pH level. The ones toward the polar zones are changing anywhere from about 0.09 to about 0.1 or so. But the question I would have for you here is this. Carbon dioxide on its own is not something that we have recognized to this point as an acid. It contains neither hydrogen nor hydroxide. So based on what we have understood about acids and bases from Chem 105, this doesn't seem to fit. And yet we see the data, and we know that carbon dioxide is a contributor to this acidification. How is that possible? And I'm not looking for an answer from you for right now. I want you to kind of ponder this as we are going through and talking about some of the things today. Because by the end of today, we should have a better answer for this than what we have going into it right now. So to better understand this question, let's take a look at some things that we already do know. So much of what our discussion in Chem 105 was all about was the definitions of acids and bases according to Arrhenius. And the reason we use the Arrhenius definitions first and foremost in Gen Chem 1 was simple. Arrhenius acids are easy to pick out. Arrhenius bases are easy to pick out because they're formula based. I can look at the chemical formula of an acid and see, hey, this starts with hydrogen, it must be acidic. I can look at the chemical formula of something that is basic and say, oh, this has a hydroxide ion on it, it must be basic. And that's what the Arrhenius definitions do. Arrhenius acids generate protons, H plus ions, in water. And Arrhenius bases produce hydroxide ions in water. And so this was the definition that we used for doing things like figuring out acid versus base for solubility purposes, identifying acids and bases based on chemical formulas. Some other definitions, these ones pertaining specifically to acids. Acids can be quantified based upon the number of acidic protons that they have, the number of H pluses that they can generate. When we have only one acidic hydrogen, we call that acid monoprotic. Most of the acids that you can think of are monoprotic acids. This ranges anywhere from nitric acid to any of the halogenated acids, hydrofluoric acid, hydrochloric acid, hydroiodic acid. This also goes into things like acetic acid, where we have just one acidic proton. Polyprotic acids, on the other hand, have more than one proton to donate and will often do so. So examples here would be things like phosphoric acid. Phosphoric acid actually has 3 acidic protons. It is considered triprotic. More commonly, we think of things like sulfuric acid. Sulfuric acid is diprotic. Carbonic acid is diprotic. Oxalic acid is diprotic. And so in Chem 1, this is the kind of stuff that we talk about. These are all definitions that we saw in Chem 105 at some point in time. We also saw in Chem 105 the concept of a Bronsted-Lowry acid and a Bronsted-Lowry base. And if you recall, when we discussed these in Chem 105, the thing that we talked about is this is the way to identify acids and bases based on reactivity. So if I'm given a chemical reaction, if I notice that there is a proton exchange in that chemical reaction, that is an indication of Bronsted-Lowry acid and base behavior. And so what we see in Bronsted-Lowry behavior is hydrogens moving from one one compound to another. So the hydrogen from hydrochloric acid goes to water, and we end up getting chloride ion and H3O plus, the hydronium ion. And so for this reason, we could identify hydrochloric acid as the acid. In this case, water would be the base. And the reason we can identify the water as a base is because under the Bronsted-Lowry definition, a Bronsted-Lowry base is one that accepts the proton. So every acid-base reaction under the Bronsted-Lowry definition has an acid and base. The acid gives the proton, the base accepts the proton. And so I don't need a hydroxide or a hydrogen necessarily to have acidic or basic behavior. I just need to have the ability to maneuver a proton from one side to the other. And so the flip side example of this is ammonia. Ammonia has no acidic hydrogens. It also has no hydroxide. So on its surface, we would look at ammonia and say, well, hold on a second, ammonia is not an acid or a base. However, when ammonia is bubbled into water, water gives one of its protons to the ammonia, and the results are the ammonium ion and the hydroxide ion. Under this definition, the ammonia accepted that proton, so it is a base, and the water gave that proton, so it is an acid. And so if you think back to Chem 105, this is how we kind of cheated around the idea of ammonium hydroxide instead of ammonia. When we described ammonia-based solutions, we never referred to them as ammonia NH3. We always referred to them as ammonium hydroxide NH4OH. And the reason why we did that was because when we referred to them as ammonium hydroxide NH4OH, there's that magical hydroxide that we can use under the Arrhenius definitions. So we took a couple of liberties in Chem 105 just to help us to identify bases a little bit more simply. So with those in mind, let's do our first question of the day. This is a select all question, so there are possibly more than one answer. But I want you to select all compounds that could be or are Bronsted-Lowry acids. All right, so based on this list, we can definitively pick off one of them as absolutely an acid. Which one would that be? So structurally speaking, formic acid here, I I just said its name. But as far as carboxylic acids, organic acids are concerned, this structure here, because of electronegativity differences, this OH bond is pretty easy to cut off. So this one is definitively an acid. The other ones, there's no claim that we can make here for letter D. While there are hydrogens, remember for acidic behavior, that hydrogen has to be able to be cut off relatively easily. We have to be able to break that bond. And the way that we break that bond easily is if there is a disparity of an electronegativity where the majority of the electrons are hanging out on the one side of the bond and not the other, making it easier to just pop off that hydrogen. Well, there are no hydrogens bonded to this nitrogen. Nitrogen is the only electronegative element on there. So B is definitively correct. D, there's no way it could be correct. And then for the other two, well, here's where it gets a little bit tough. Tellurium's not terribly electronegative. So we're going to have problems with electronegativity difference for bonding. First instinct would be that this one's no good. And while there is definitely electronegativity here, where the nitrogen is going to pull electrons away from the hydrogen, this one is kind of the biggest question mark. So interesting. So, the response from the question, I didn't write the question. The response from the question is definitely B, which we knew. I'm not surprised that they said that C was wrong, just because based on what we know about nitrogen, what I want you to think about is we showed that example of ammonia. The ammonia wasn't acting as an acid. The ammonia was acting as a base. So the electronegativity difference between the nitrogen and the hydrogen really isn't a big enough difference for that nitrogen to hydrogen bond to break easily in water unless it was severely influenced. I'm surprised by the answer of tellurium. I really am. I'd like to see what logic they applied for that one. So this ended up being incorrect, which, but this one, I mean, I guess the argument that they're making is that the H2TE is a lot like water. But like I said, I feel like that's a hard sell because the electronegativity difference is not that great. In fact, I think hydrogen is more electronegative. So we might agree to disagree on that one. All right, let's try the next one. Select all the molecules that are Bronsted-Lowry bases. Now, again, under the Bronsted-Lowry definition, the base has to be able to accept a hydrogen. All right, this one I feel is a little bit more clear cut. Okay, the majority of you have picked ones I would pick as well. I would have picked the amine ion there. I would have picked the telluride ion. The only question I would have about this one right here is this is its structure. The question would be, where does the hydrogen go? Because one of these lone pairs would have to be replaced by a hydrogen to do that. And that would pretty considerably destabilize that molecule. So that seems far less likely. My answers for this problem were A and B, because we can see if I add a hydrogen here, I'm going to get to ammonia. And we know that the ammonia molecule is stable. And if I add a hydrogen here, I'll be at the intermediate state between H2E and the telluride ion. So that's definitely in the right direction as well. And yes, they agree with us on that one. So good job for them. Okay, so let's talk then about a phenomenon that we definitely have experienced and comes to light in Bronsted-Lowry definition, and that's water. We can call water amphiprotic. Now, what does that mean? Well, let's break down the word. Amphi, two natures. Just like an amphibious vehicle is suited for land and water. An amphibian can live part of its life on land, part of its life in the water. Water is an amphiprotic molecule. It is capable of either donating or accepting hydrogen. And because of this, water is actually capable of reacting with itself. The amphiprotic nature of water is such that water will actually react with water. And one of the waters will donate a proton to the other. And the net result is we get hydronium ion and hydroxide ion as a result. Now, one thing that we can note out of this is a reversible reaction. It is equilibrium. And the value of that equilibrium constant would be equal to the concentration of the hydronium multiplied by the concentration of the hydroxide. Now, this little equilibrium expression is going to be at the heart of what we do in this chapter. So much so that this equilibrium constant gets its own subscript. It is Kw. Why W? Because it's the equilibrium constant for water. So I want you to put a pin in that particular equation because we're going to see it come up a lot over these next 3 days. And in fact, we'll see it come up a lot in the next chapter as well, because the next chapter is all about just more aqueous kinds of chemistry. So that expression, Kw, this is what is known as the autoionization of water. And at 25 degrees Celsius, the autoionization of water yields a Kw of 1 times 10 to the negative 14th, which, if you carry it out and solve the ice table that would come as a result of this, each solution, each part of it, the hydronium and the hydroxide in pure water would be 1 times 10 to the negative 7th in molar. And it's for this reason that we really haven't mentioned it to this point. Because in terms of acidic or basic behavior, 1 times 10 to the negative 7th molarity is a big fat nothing. It is not going to impact the acidity or the basicity of whatever substance is present with it. But there are a couple of things that we can say. Since acidic solutions are going to involve H plus being donated to water to make hydronium ion, in acidic solutions, the hydronium concentration goes up, which means that the hydroxide concentration is going to go down in order to maintain this constant Kw. And so what we see is that in acidic solutions, the hydronium concentration is greater. In basic solutions, water acts with the base to make hydroxide and the conjugate acid of that base. And so what we see is that the hydroxide concentration goes up. And so in basic solutions, we have a higher proportion of hydroxide compared to hydronium. And so just in summary here, the autoionization of water will always result in the presence of hydronium and hydroxide. In pure water, those two concentrations of hydronium and hydroxide are equal. When we are not in pure water, when we're in acid or when we're in base, we'll see that they will shift accordingly. Higher hydroxide for base, higher hydronium for acid. But note, the concentration of the other never completely disappears. We might run it out to as negligible as you can imagine, but it's never truly gone. Now, before we move on to talking about acids and bases themselves, I want to make a distinction. The term amphiprotic refers to the reaction of a substance as either an acid or a base. The term amphoteric sounds similar, and in a lot of ways there is crossover between them. Sometimes they are used interchangeably, but we need to make an important distinction. Amphoteric species are capable of reacting with either acids or bases. This is different than something being amphiprotic. An amphiprotic substance is capable of acting as an acid or a base. There's a difference between acting as them or reacting with them. Amphoteric substances react with acids and react with bases. Amphiprotic substances can act as acid or base depending upon their circumstances. So in the book, you'll see that there's a focus on some amphoteric oxides. So for example, lead 2 oxide is capable of reacting with hydrochloric acid. The results are lead 2 chloride and water. We can also see lead 2 oxide reacting with potassium hydroxide to make potassium hydrogen lead 2 oxide. The key attribute to each of those is that in being able to react with acids and bases in that kind of way, we have two different ways of getting lead from its oxide counterpart. Why that's important is because a lot of natural metals that we get usually come out of the ground in ores, rocks that we dig out of the ground. And most of those metal samples are in oxide form. So if, for example, I wanted to extract lead out of these lead ores, I would need to find a way to get the lead out of its oxide form. I would need to react it in some kind of way. And so what amphoterism does is it gives us the ability to, depending upon the circumstances, we can react that ore with acid or we can react it with base and get ourselves closer to the product. We see an example of this here. So in base, we can actually get the whole thing to dissolve. It goes aqueous on us. And if it's aqueous, we have ways of extracting it either electrochemically or as we've seen in the qualitative analysis labs, we can separate it using chlorides and then isolate it using complexes or some other means. What we'll find is that many transition metals are amphoteric. They're capable of reacting with acid or base. Every transition metal in period 4, so that would be the 3D block. So starting with scandium and ending at zinc. All of those are capable of amphoterism. But what we also see is that some main group elements, especially those that are close to the semi-metals, have amphoteric properties as well. Aluminum is a classic example of this. Aluminum is easily dissolved in acid. It's also easily dissolved in base. And so the takeaway from this, because again, if you've heard of these terms, you've probably heard them used almost interchangeably. And what you need to understand is that they aren't truly interchangeable terms. When we're describing water and other amphiprotic molecules that are capable of being acids or bases, those molecules are also amphiprotic and amphoteric. But you'll never see lead-2 oxide acting as an acid. It can't, it won't, it doesn't. We can see it acting as a base in certain contexts. So you can look at this and say, well, hold on a second, isn't it acting as a base right now? Didn't the hydrogen attach to that oxygen? Isn't that acid-base behavior? And you're absolutely correct. It is. But this is not acidic behavior here. In order to act as an acid, the lead oxide had to give up a proton. It has no protons to give. So the two terms are not interchangeable. But there is, if we want to think about them as Venn diagrams, the amphiprotic and amphoteric Venn diagrams do have a lot of overlap in between. And so here are just some examples of some main group elements that are capable of forming these amphoteric oxides. I made mention of aluminum already, but we can see tin and lead are very capable of this, bismuth and beryllium. So if you've got elements that are kind of hugging that staggered staircase and yet are not considered transition metals in the traditional sense, they do exhibit this amphoteric kind of nature, especially with their oxides. All right. Last thing that we want to talk about in this first hour. It's a definition that kind of puts everything together. So this is a new thing. We did not talk about Lewis acid-base theory in Chem 105. But what I want you to think about as far as acid-base theory is concerned is you can think about these acids and bases almost like a series of concentric circles. The Arrhenius definition was the most restrictive. It was the most specific. In order to be an acid, you had to have a hydrogen. And that hydrogen had to come out in water. And then Bronsted theory says, well, hold on a second. What if we don't have the water? What if we just look at, does a molecule give away a hydrogen or take a hydrogen? Lewis theory takes away the kind of the last barrier. What if we don't have a hydrogen? Can we still describe acid-base behavior even if there are not hydrogens to be gained or lost? And the answer to the question is yes. What we need to look at instead are electrons. So by definition, a Lewis acid is one that accepts a pair of electrons from a Lewis base. Now, the comforting thing in this particular mindset is that Lewis acid-base theory automatically accepts everything that we thought about in terms of Bronsted-Lowry theory. And we'll show you an example of what we mean by that. So let's take this idea of the ammonia reacting with water. Under the Arrhenius definition, ammonia could not exist as a base. But under the Bronsted definition, we talked about the movement of this hydrogen from the water to the ammonia. Basically, what we're looking at now is, well, what if it isn't the hydrogen that's moving? What if it's the electrons that are moving? And so we look at this lone pair of electrons on ammonia, and we see that that lone pair of electrons is going out and grabbing this hydrogen. Since the hydrogen now has its 2 electrons from the lone pair that it just absorbed, the electrons that were in this bond go back into the oxygen as a lone pair, and we have our products, the ammonium ion and the hydroxide ion. Every other Bronsted acid-base example that you can think of would work the exact same way as this one does. And for those of you that have to move on to organic chemistry, get used to this idea of electrons moving around and this arrow notation for showing how electrons move from one atom to another and form bonds between one atom and a different atom. Because when you get into organic mechanisms and trying to describe how does this organic molecule get from reactant to product, what you're going to find is that this electron moving mechanism kind of diagramming is the way that you explain how those things happen. But what Lewis theory allows us to do is it allows us to move off of hydrogen. So the example that we just did still involved a hydrogen, right? We had the lone pair of the nitrogen going out and grabbing a hydrogen off of a different molecule and bringing it in. It's a Lewis explanation for what we saw in Bronsted theory. But what about a reaction like this, where the ammonia is going out and grabbing an entire molecule rather than just an individual atom? Under Lewis theory, this is an acid-base reaction as well. Ammonia, being the electron mover, is acting as a base. Boron trifluoride, being the acceptor of that extra pair of electrons, is a Lewis acid. So to kind of summarize this into something that's a little bit more digestible, Lewis acids accept lone pairs of electrons. So under Lewis theory, forget hydrogen. Focus on the electrons. And from the electronic standpoint, it's the opposite of what we were talking about with protons. Under Bronsted theory, the proton donor was the acid. Under Lewis theory, the electron pair donor is the base. But the whole point of a Lewis acid is we're getting a new bond to form. Every Bronsted-Lowry acid is also a Lewis acid. They all fit under that definition. But Lewis theory expands acid-base to include other molecules that did not previously fit under that umbrella. Lewis bases, on the other hand, they are those paired donors. And so they're throwing out their electrons and they're grabbing up a new molecule, a new atom to make a new covalent bond. Under Lewis theory, everything that was a Bronsted base before is a Lewis base. But this does allow for the expansion of base theory to apply to more than just hydrogens and hydroxides and the movement of protons. Now, we can pick up some visual signs. What are some ways to tell that we have a Lewis acid? Three big ideas. First of all, Lewis acids are usually one of these three, and sometimes multiple of these together. If I have a cation, so if I have a positive charge, that's a usual sign that I'm electron deficient, which means I'm willing to take in that extra pair of electrons to supplement the electrons that are already in my octet. This middle one's a big one. If I have an incomplete octet. So if I'm electron deficient, because I only have 6 electrons around me instead of the normal 8, I'm much more prone to accepting that extra pair of electrons as a Lewis acid. And metallic. Metallic elements tend to be very good Lewis acids. On the other hand, Lewis bases, we tend to see anions. Why does that matter? Well, anions usually have extra lone pairs of electrons, and so they're capable of throwing out that extra pair of electrons to make a new bond. If we have completed or expanded octets, same thing. I have an abundance of electrons, that those extra electrons can be used to go out and make new bonds. And where we see this primarily is in nonmetals, because nonmetals usually tend to have full octets with extra electrons. So let's stop here for our first hour.